start to build together mass spec, IR and NMR data. There's loads of questions in here you don't need for the new spec, so apologies about that, but we're going to concentrate on the questions like this one. We have to work out the structure. You can pick up marks without working out what the actual structure is quite often, but it's worth tackling question 1A, I think. So why would you bother to do analytical techniques? Simply, this is a really easy question, but the whole point is it's determination of structure. That's the main reason we will do it. That's the word structure in there. And you're trying to find out what it is you've made, or it could be working out the purity of something. So you can do this stuff quantitatively, and they're probably the main reasons for that. I think you know what happens when molecules absorb infrared. Only molecules that change their polarity can absorb infrared. Change their polarity when they bend or stretch or change angle. So explain what occurs at molecular level. Essentially, the bond angle changes, so OSO angle changes, which changes the polarity, which means it can absorb IR. The length of the bonds might change. And by the way, all of these mark schemes I'm going to share with you before the end of the lesson. And that causes, either of these two things would cause the polarity of the molecule to change. And that's why diatomic molecules like N2O2 don't absorb infrared. If we need to spend more time on that, we can do, but I'm not going to do that right now. Right, so let's have a look then at the kind of questions you're going to get, which I want to spend more time on, which is these kind of analysis questions. And there's loads and loads and loads of these that I've got for you. So we're going to look at these spectra and start to get familiar with them. So this is looking at IR spectra. If you're looking at IR spectra, you've got to be citing what bond you can see. So it might be you can see, for example, a CH or a C double bond O or an O, or an OH. And so you'd say that in an exam and what it is that you can actually see. And it's good practice to use your data books here, but you'll become quite familiar with the key peaks. So you should always and really easily spot the broad peaks around about the 3000. There's a broad one here, and there's a broad-ish one here which are worthy of note, so I think it's worth picking out those. And we're also looking at these molecules up here. Just one sec please, let me just take you through stuff. The other things of interest in here are the CH is buried underneath there. You can see the sharp one's about 3000, and there, and in all molecules, including that one. And the other common interesting peak is worth noting and always writing about is one at about 1700, which is a C double bond O. So it's nearly always those peaks you've been looking for. There's sometimes other ones, and you should then be able to pin the spectra to the molecule, be really comfortable with turning that into its structure. You should know by the time you get to your exams, and hopefully soon, that that's an ester straight away. That's a tertiary alcohol, and that's a carboxylic acid. That should be pretty straightforward. So how are you going to get 5 marks for this question? What you've got to do is make the connection. So A is this molecule here. You'd expect to see a peak. I think in the data book it will say something like 2,500 to 3,000. So say what you're seeing in the data book, and that would be the OH in carboxylic acids. And I think in your data books, can you just check your data books for me, because they're different every year or every change. The OH in carboxylic acids is slightly different from the OH in alcohols. Is that what you've got? So this one is, look, it's slightly different to the one in spectrum 2 there, the OH. So it's the OH in COOH is there. You've also got, well, that already tells you what the molecule is, because it's the only one with a carboxylic acid, isn't it? But you have also got, I would certainly, even though it doesn't say it in the mark scheme, I would definitely highlight the fact that there's a C double bond O there. It's not a carbonyl because it's part of an acid, but that's at about 1700 centimeters to -1, or write down what the C-double-bond-O in carboxylic acid is from your data book as well. And we can clearly link that one to spectrum 1, right? So there we go. So a couple of marks for that. Well, so you get 1 mark for getting each of these 3 boxes filled in correctly, and 1 mark for getting these 3 filled in correctly. I'm not sure what the 5th mark is for. Can't work it out. You get 2 peaks for this one, I think. So B, look here, we've got an ester. So the key thing there is we've got a 1700 to 1750 centimeters peak, as it says in the data book, and that's your C-double-bond-O. And then the key thing here is that there's no OH peak. And this is why we're doing some exam questions, so that you see what it is you need to say. Would it have been obvious to you to say what you don't see? And that's just as important as what you do see, I would say. The only one without an OH peak is spectrum 2, beg your pardon, spectrum 3. That tells you that it must be B. So you get 2 marks for that, and it's the second mark there I think you would lose without being that, without doing this practice. C is clearly just an alcohol, and that's the only one that's left, which is spectrum number 2. And again, you've got a peak at 3,200 to 3,600, which is the numbers from the data book. Centimeters to -1, which is wave numbers OH. You could say, I would probably, it doesn't say it in the mark scheme, but no C-double-bond-O as well. Right, so you can approach this in slightly different ways. So you're starting to pick up the way that you'd approach these kind of questions. As much information, you can do that without having any idea what the answer is, right? What does the spectrum show you? Can you read off a graph, basically? And then we've got question 2, different question altogether. By the way, I'll mention it now, skip that question there. We don't need to know about body scanners, so some of you might have heard of MRI machines in hospitals for looking inside your body and whatever. Right, let's go through this together. I do have the mark scheme in front of me, but I'm looking at this live with you. Hello. Yeah. So a feature of some proton NMR spectra is the electron withdrawing effect of electronegative atoms. I told you in lessons that causes the peaks to be pulled to the left. It increases the chemical shift. But it tells you that on the data books anyway. Look at this spectrum beneath, which is compound D. You're told it's got a molecular formula of C4H8O2. This is where I'd get the scrap paper. I'd immediately see this and go, right, I need some scrap paper. I don't want to be making rough notes, thank you, on here. I want to get the answer in the small box given to me in the paper if I can. So there's not, believe it or not, there's not an enormous number of molecules that have got C4H8O2 and contain a C-double-bond-O, because you're told that in the question. So you can start brainstorming it a little bit. And you're also, before you start doing that, write down what you definitely know about this. So remember, there's 4 bits of information we can get from a spectrum. We'd say those bits of information here. So I'm not using the mark scheme yet. I'll come to that in a second. We've got 3 peaks. So 3 hydrogen environments. You see, we're hoovering up easy marks. This is so easy. It's literally every single person who does IB can get these marks. The ratios of them are 3 to 2 to 3 ratio. So in other words, there's one environment which is of H's per environment. And because 3 plus 2 plus 3 adds up to 8, we know there's not twice as many hydrogens as that, and we're told we've got a molecular formula of 8 hydrogens. So right, that's getting easy. And then we look at each each peak in turn. And personally, what I do when I do these questions, and bear in mind I'm doing this while sort of live with you, So I'd label them A, B, C for the examiner, or you can label them with their chemical shift, probably both. There's no harm in doing that. So what do we know about A? So it's a singlet. So no H on adjacent carbon. And then just mention n+1 rule. We're showing our examiner that we know what we're talking about here. Hopefully you can read what I'm writing. And it's 3 hydrogens. So it's going to be a CH3 next to a carbon with no hydrogens on it. So we're just starting to build the picture without having any idea what the molecule is. B is just about a quartet. It's a pretty grubby quartet. And it's a CH2. And there must be, therefore, in total 3 hydrogens on adjacent carbon, and then n+1 rule. Don't give the examiner any chance to give us knock us marks off. And the last one is, again, it must be a CH3, and it's clearly a triplet this time, nice neat triplet. And so that's a CH3 adjacent to a CH2. Okay, again, n+1 rule. So already, so on my scrap paper then, I'm going, all right, well, I know there's a CH2, CH3 in there, because there must be, the CH2 must be attached to a CH3, and there's another CH3 which is attached to something with attached to a carbon with no hydrogens on it. Now, we should also be looking at the chemical shift, remember. So we've got the number of hydrogens, and we've got the splitting pattern. So this obviously is printed half size, so I'd probably be putting in here the ppm as well. So if you can squeeze it in, 3.6-ish parts per million chemical shift. Therefore, and that would suggest to me that that's a CH3 directly connected to an oxygen, according to your data books. I think if you look that up, obviously you don't know those chemical shifts yet, but you'll start to get familiar with them. And the CH2 there has got a chemical shift of, what's that, should we go for 2.5, 2.3-ish, you reckon? Centered around 2.3 parts per million. And therefore, that CH2 is probably next to a C double bond O. So we're starting to build the picture. So we've got CH3 next to a CH2 next to a C double bond O. And we've got a CH3 next to an oxygen. And we've got a total of 4 carbons. 1, 2, 3, 4. Make that clear. And 2 oxygens. 1, 2, and 8 hydrogens. Bingo, I think we've cracked it. By Jove. I reckon it's that molecule. And I know, because I've got the mark scheme next to me, that I'm right, which is handy. But you also get away with the ester the other way round, even though it's obviously wrong. Because they're nicer than you might imagine, the IB. And that's how you tackle one of these questions, and you get all the marks. The way that it's marked is 1 for the right answer, only 1 for the right answer. Saying that there's 3 peaks in a 3:3 ratio gets you a mark. Everybody can do that, even if you have got no idea what's going on. Mention you've got a triplet, singlet, and a quartet, and the explanation for those, as I set out, n+1 rule, number of hydrogens on adjacent carbons. Even if you've got no idea, you can pick up the mark for that. You get half marks without having a clue what the answer is. And, you get a bonus mark if you get the ester the right way around, with the oxygen there next to the CH3 as I've drawn it. So you do get the extra mark for that way around. Okay, so that's how you approach these. And some of them are more generous for the working out than that even.